let's look at some nonlinear stuff here. So let's say we've got the following system. Sorry, not nonlinear, non-homogeneous. Apologies. So Co-17C. Today is February 23rd. You know what's great about the number 23? One of my favorite facts, one of my favorite math facts is that 2 to the third plus 3 to the second plus 2 times 3 equals 23. Just kind of love that one. Not important at all, but just neat. Anyway, moving along. Let's say we have the following linear system of differential equations. So we have that. I'll try to use his notation. It's so unnatural for me. So we have x1 dot equal to negative x1 plus 4, and x2 dot equal to x1 plus 2x2. Written as a matrix equation, this becomes the matrix, the vector x dot equal to the 2 by 2 matrix. So my coefficients are -1, 0, 1, and 2. Right? There's no x2 there, so its coefficient is 0. Times my variable vector x1, x2 plus the b, the extra vector that's not quite there. That is there, the 4, 0, the part that's making it inhomogeneous or non-homogeneous. This is our a times x plus b. And so when we solve a system like this, I might be presenting it slightly differently than he has, but the process is still pretty much the same. We're going to find the equilibrium. I will point out, as far as like a conceptual thing, how you find the equilibrium is super straightforward. You're just finding where each derivative is equal to 0. You're finding where things aren't changing. So to find the equilibrium, we're just setting negative x1 plus 4 equal to 0 and x1 plus 2x2 equal to 0. When we do this, we end up getting x1 equal to positive 4. And if x1 is equal to 4, we can plug that in here and get 4 plus 2x2 equal to 0, which is going to mean that x2 is equal to -2. There's our equilibrium, which is not the origin, right? Every time we've done this so far, the equilibrium has been the point 0, 0. This is kind of the first time where we're seeing something other than that. Okay. And for those of you walking in, I should have labeled this. This is a non-homogeneous. Labeling things is good. Non-homogeneous, I can spell. Non-homogeneous linear system of differential equations. Cool. All right. So to solve a system like this, what we typically do is we kind of reimagine it. We're going to make a substitution. We're going to let essentially y equal x minus r. I'm never good at making up a good name for this. I feel like there's a good name for it. I think he called it like C or something in class. Yeah. I don't love that though, but fine. Sure. And it was minus, right? I think. Yeah, that's how I'm writing it. I think he writes things weirdly. I'm not gonna lie. I'm just like, what are you doing? Okay. So in this particular instance, we're gonna say that our new vector y1, y2 is equal to our old x1, x2 minus our equilibrium here, our 4, -2. What we're really doing is we're going to add it over there, and we're going to get that x1, x2 is equal to y1, y2 plus 4, -2. And then if we take the derivative, interesting here. Yeah, sure. Yeah, that's fine. Okay. Sounds like something weird. Okay, cool. So then we've got our new set of equations. X1 equal to Y1 plus 4, X2 equal to Y2 minus 2. And now let's differentiate both sides. So sorry, I know I keep going back and forth here. There's a little bit of, yeah, that's funky. All right. Sure. So if we differentiate both sides of this, look what we've got. Take the derivative, we differentiate. With respect to time, I'm going to use the terrible notation, even though I don't love it. We're going to have x1 dot equal to y1 dot, and the derivative of 4 is 0. Similarly, we're going to have x2 dot equal to y2 dot minus 0, which is nice. And then what we can do is we can say, well, look, we can replace the x1 dot, what it's equal to. X1 dot is equal to negative x1 plus 4. But then x1 is equal to y1 plus 4. So I can really write this as negative y1 plus 4 plus 4. The minus distributes and the 4's cancel, and you just get negative y1. I know it feels like we're kind of doing just like making shit up, for lack of a better word. It feels like we're kind of just doing something weird. We're gonna get somewhere, I promise. Just bear with me for a second. We're gonna replace what x2 is equal to with x1 plus 2x2. And then we're gonna replace each of the x1 and x2's with what they're equal to in terms of y. So we're gonna get x1, which is y1 plus 4, plus 2 times x2. Let's just multiply that and get 2 times y2 minus 4. Again, things cancel, and we just get y1 plus 2y2. So all this to say, we essentially get the same system of differential equations. Our new system here, our new homogeneous system, is that y1 dot equals negative y1, and y2 dot, the derivative of y2 with respect to t, is y1 plus 2y2. Or writing it in the matrix notation, y dot equals the matrix negative 1, 0, 1, 2 times y1, y2. The sum up here is that making this change, the substitution, gives you a homogeneous differential equation, and the coefficient matrix is exactly the same as it was. We still have the same A being negative 1, 0, 1, 2, negative 1, 0, 1, 2. The difference here is that we don't have to add on this other part here that's making it inhomogeneous or non-homogeneous. So typically, people kind of bypass all of this that we just did. And they're like, okay, great. I'm going to say that, like, so just for example, like what the work we really kind of would have done in a normal situation is we would have started with this, and then we would have said, all right, we're going to let y equal x minus the equilibrium, which we often call like x hat. And then instead of having x dot equal to a times x plus b, we instead get y dot equal to a times y. Same A. And we just saw that. We did all the work that shows, oh yeah, look, we had a times x. Oh, sorry, you can't see that. Apologies. We had x dot equal to a times x plus b. We did a substitution, and our new equation was just y dot equal to a times y. Awesome. So what I'm really trying to say with a lot of words and a lot of explanation is that you don't have to show all these steps that we just showed. You can jump to the assertion that your homogeneous system of equations using y will have the same matrix A. Great. And then, oh, go ahead. Yeah.
skip everything.
We can skip all the things we just did, but we need to do it at least one time so we understand why we're able to do the skipping later on. It's kind of like how when you learn the limit definition of the derivative or the power rule, and you do it the long way the first couple times to understand what you're doing, and then you do the short way. You're like, we learned how to do it the short way because of the long way. We still needed to do it the long way to know that that's what we're doing. You're like, we could have skipped the long way. No skipping the long way. Not with me. So then it's the usual kind of deal. We're gonna find the eigenvalues, find the eigenvectors, do the general solution. So let's do that. Oh, it's something I've been not saying a lot of because we haven't seen a lot, but I think I said it once or twice. For this matrix here, without writing anything down, every single one of you should be able to tell me what the eigenvalues are. Thank you. Yes, awesome. For lower triangular matrices where you have a 0 up here, or for upper triangular matrices where you have a 0 down there, or for diagonal matrices where you have a 0 up there and a 0 down there, the eigenvalues are always the diagonal entries. If you're not sure about that, find them. Do the work. Do determinant of a minus lambda I equal to 0, multiply it out, and you'll see that those are your eigenvalues. But I'm not going to do that right now. I'm going to move on. So now we're going to find the eigenvectors. For lambda 1 equal to 2, we're going to have a minus lambda I times my eigenvector equal to 0. So it's going to be, let's see, I'm subtracting 2 in each of the diagonals. So I have -1 minus 2 is -3, 0, 1, 2 minus 2 is 0, times the eigenvector I'm trying to find. Yeah, sure. I don't love that notation. It's fine. Okay, so either way you multiply this out, you either get -3 times v1 equal to 0 or 1 times v1 equal to 0. So we know we're for sure getting the first entry equal to 0. And when one of the entries is 0, the other one gets to be whatever you like, except for what you're not allowed to pick 0. What are we going to pick? The unexciting one. Yeah. You can pick anything, but the normal choice is to pick 1. And then similarly, we let lambda 2 equal -1. So now if we do this, we're going to get -1 minus -1, which is 0, and then 0, and then 1, and then 2 minus -1 is 3. So then we multiply this by our v1, v2 equal to 0, 0. The first row doesn't help you at all. 0 times v1 plus 0 times v2 equal to 0 is always true. And it would be true no matter what you picked for v1 and v2. So focus in on the row that actually matters. 1 times v1 plus 3 times v2 equals 0, or 3v2 equals -v1. So pick v2 equal to -1 and v1 equal to +3. Or vice versa, -3, +1. Either way. Or something totally off the chart, like 6, -2, or 20. 20 stupid. You could use 20. You could do 20, comma, -23. That would be a terrible choice. But any multiple, right? Any multiple of this eigenvector is also an eigenvector. So then we're going to write our general solution here. For a general solution, which is the usual y, right? We're solving the general solution for y. We're going to get y of t equal to c1 e to the lambda 1 t v1 plus c2 e to the lambda 2 t v2. If you ever have to like find the general solution, which I imagine you will on your final, I do recommend writing this formula out just generically if it's not already given to you, so that the person who is seeing your work knows that at least they know what the formula is. And then if you mess it up along the way, they'd be like, well, there's some of this partial credit because they knew the right thing. They just maybe made some errors along the way. All right, so subbing in what we know, we're going to have that y of t is equal to c1 e to the, I said lambda 1 was 2. So 2t times v1, which we ended up being 0, 1. Do you make sure you pair the correct vector with the correct value? Plus c2 e to the lambda 2 was -1 times t times our eigenvector, which was 3, -1. I should also point out, we certainly know what sort of equilibrium we have. Is it a node? Is it a spiral? Is it a saddle? Definitely a saddle, right? We have opposite signed eigenvalues. -1 and +2. So not that I'm asking about that, but I'll just point out we have a saddle. Is that stable or unstable? Generally, we think of a saddle as being unstable. There is one line or direction of stability, but for the majority of ways you can approach the equilibrium, it is unstable, and so you get pushed kind of away from it. So if someone asks you about the stability of something and they're just saying like, say it's stable or unstable, and you get a saddle, say it's unstable. Okay, sorry. Grab my note here, sure. So now what we're gonna do is we're gonna substitute back what the y1s and the y2s were equal to in terms of x1 and x2. So I'll point out here, let's actually write this out a little bit more here. So what we have here is that y1 of t equals none of this first part, right? I'm looking at the first row, plus 3c2 e to the negative t. That's y1 of t. And we'll fill in what that's equal to in a second here. And y2 of t is equal to c1 e to the 2t times 1 plus c2 e to the negative t times -1. I should have not written the plus sign there. Oh well, too late. And then if we look back a couple pages, we can see that where'd it go here? That y1 is equal to x1 minus 4. And that y2 is equal to x2 plus 2. So now we can solve for x1 and x2. So we're going to get, yeah. The 3 came from right there. Right, so I have, so y1 of t is equal, right, the first row, and I'm being lazy here, not writing it out, but if you really wanted to, you could write this as one vector. You could write it as c1 e to the 2t times 0 plus c2 e to the negative t times 3, and then down the second row would be c1 e to the 2t times 1 plus c2 e to the negative t times -1. So y1 being this is just coming from that multiplied by 3. That clear? Okay, good. So then we can solve for x1 and x2, and we're going to get x1 equal to, how do I want to write this? Let's make sure I write this in the nicest way possible here. Yeah. 3c2 e to the negative t plus 4, and x2 of t is going to be c1 e to the 2t minus c2 e to the negative t minus 2. Or written in a more kind of normalish way, we could say x of t is equal to our general solution here, c1 e to the 2t times 0, 1 plus c2 e to the negative t times 3 -1 plus 4 -2. Or essentially, the general solution of just the matrix A part, and then you add on your particular solution. That's kind of it. So I know we've done a lot more work than we needed to here to do this, but it's showing us that, oh yeah, all you have to do is find the coefficient matrix A, deal with that like you normally would, and then whatever your general solution to that is, add on your particular solution that you found in the beginning, your particular equilibrium you found in the beginning. Kind of nice. So should we do one more? I think we should do one more. We'll do one more the fast way, not the long way. Okay. Yeah. Is it about this? Okay. Let's do one. We'll do one more of these, then we can look at that, if that's all right. But you should go ahead and find it if you can. I also have the book here if you know which number it is. So let's look at this next example. Similar idea. This is where we're also going to throw in an initial condition. So we have dx. Sorry, couldn't help it. I'm gonna use x's and y's. I don't want to use x's and y's actually. That doesn't do. Yeah, that'd be a stupid choice, James. Don't use x's and y's here if y is going to be your thing. You're going to make a substitution for it. So dx1 dt is negative 2x1 plus x2 plus 4, and dx2 dt is x1 minus 2x2 plus 1. And we're given that x1 of 0 equals 0, and x2 of 0 is also equal to 0. How boring. Okay. Equilibrium is a little bit spicier this time. We're not just getting to say that x1 equals something and then plug that into the other one. We actually have to solve these systems simultaneously. And I'll remind you that if you set this equal to 0, it's essentially the equation of a line. Same deal here. So you're really just finding where these two, hopefully non-parallel, lines intersect. If they're parallel, you got problems. They're not parallel. They're not parallel? Yeah, they're actually like perpendicular, I think. So I'm going to solve for one of these variables. I'm going to set this equal to 0. So setting this equal to 0, I'm going to say, let's do x2. Oh, I could have just done elimination. Oh, well, too late now. x2 equals 2x1 minus 4. Plug that back in here. And then we're going to get this is going to be x1 minus 2 times 2x1 minus 4 plus 1 equal to 0. Solving that, we've got x1 minus 4x1 is going to be minus 3x1. And then minus 2 times minus 4 is plus 8 plus 1 equals 0. So 9 equals 3x1. So x1 equals 3. And then plugging that back in up here, we're getting x2 equal to 6 minus 4. So x2 is going to equal 2. So our equilibrium, the thing we're going to add on to our general solution at the end of the day, our equilibrium is 3, 2. Say that one more time. Should I say that? Say which thing are you talking about? That's not a 4. That's a 9. Yeah, fair point. So the equilibrium, which people often call x hat, is 3, 2. Okay. Cool. So we'll get there in a minute. So then what we're going to do is we're going to find the solution to the general solution to the 2 by 2 matrix, usual deal. So we're going to say, great, our matrix A is just negative 2, 1, 1, negative 2. Sadly, we don't have the nice situation where you just get to see the eigenvalues right off the bat. So we actually have to do the work here. So we're going to get determinant of A minus lambda I, which is going to be negative 2 minus lambda 1, 1, negative 2 minus lambda. I will point out, if you notice that the diagonal entries are the same, you can solve this without having to multiply it all out and use maybe the quadratic formula. What you can do instead is say, well, that's going to be negative 2 minus lambda times negative 2 minus lambda minus 1 times 1. But since this is the same thing, you can say, oh, I've just got negative 2 minus lambda squared. Add the 1 to the other side. And since that's a positive over there, we're not going to have imaginary situation. We're going to be totally real. That means negative 2 minus lambda is either equal to the positive or the negative square root of 1, which I should not write. I should just write 1 because the square root of 1 is 1. That means negative 2 minus lambda equals plus or minus 1. And then I would probably say negative 2 plus or minus 1 equals lambda. So negative 2 plus 1 is negative 1. Negative 2 minus 1 is negative 3. Those are my eigenvalues. What kind of equilibrium do we have? Everybody. Stable node. Right? Stable node. Let me double check my, I'm sure the eigenvalues are right. Yeah, they're right. Okay. You can check if you really want to, right? If you plug negative 1 back in there, negative 2 minus negative 1 is negative 1, and negative 1 squared is 1. If you plug the negative 3, negative 2 plus 3 is positive 1, positive 1 squared is 1. So good. Okay, so then we have the eigenvalues, I find the eigenvectors. Let's do that real quick. Blah, blah, blah. So let's say that doesn't matter. So if lambda1 is -1, then our first eigenvector is going to be, let's see, I'm going to have -2 minus -1, which is -1, 1, 1. -2 minus -1, which is -1. That's -2 minus -1 is -1 is. Yeah, that's right. It just feels a little dicey. And we set that equal to 0, 0. We're going to get V11 equal to V12. Or I should say negative V11 plus V12 equals 0. And then I solved it. And then I got the eigenvector of 1, 1. And then similarly, for lambda1 equal to -3, do the same sort of deal. -2 minus -3 is 1. So I'm going to get the matrix 1, 1, 1, 1. Again. So we're going to get the first thing V21 plus the second thing V22 equal to 0. So they're going to be opposite signs of each other. So we're going to get either 1, -1, or -1, 1. I would probably generally choose to pick the first thing being positive if one of them has to be negative. All right. And then let me make sure I'm not doing anything stupid here. No, I think we're good. Let me double make sure I'm not doing anything stupid here. I will be totally frank. This particular topic used to really kind of throw me. So I'm always like, let me double check my work, make sure I'm doing it right. But I think we're good. So then our general solution here, I will point out we didn't actually write down the substitution. Right? I didn't write y equals x1 plus something or y equals x2 plus something. I just kind of said we're going to do the thing. So our general solution for the y's that we didn't write would be that y of t equals c1e to the lambda1t v1 plus c2e to the lambda2t v2. We jam in our lambdas and our v's, and we get that the general solution for the substitution is c1e to the lambda1, which was -1, t times v1, which was 1, 1, plus c2e to the lambda2, which was -3, times t times v2, which was 1, -1. And then the x thing, you just take that and you add on your particular solution, your equilibrium is what I should really call it, not your particular solution. So if that's y, then we get to say that x is just c1e to the -t times 1, 1, plus c2e to the -3t times 1, -1, plus it's time for church, 3, 2. Right, it was 3, 2? Yeah, it was 3, 2. And that's the correct thing. That is the correct solution. And then whoever wrote this didn't finish their work. We have to find C1 and C2. Right? Because we were given initial conditions. We were told that x1 of 0 and x2 of 0 were both 0. So then we can plug in 0 for everything. When I say everything, specifically, I mean we're going to have x1 of 0, x2 of 0, which are both equal to 0, equal to c1e to the 0 times 1, 1, plus c2e to the 0 times 1, -1, plus 3, 2. And then we can solve for c1 and c2. Which is never my favorite thing to do, but we can do it. So we got 0 equal to c1 plus c2 plus 3, and 0 equal to c1 minus c2 plus 2. And the easiest thing I can see to do right off the bat here is to add those equations together to cancel out the c2s. If you see an easy thing to do like that, where you can add the equations or subtract the equations to make one of the two c's cancel, do that. So add these together, you get 0 equal to 2c1 plus 5. So c1 is going to equal -5/2. And then plug that back into either equation, and you're going to get, so let's plug it in the first one, 0 equal to -5/2 plus c2 plus 3. -5/2 plus 6/2 is 1/2. So 0 equals 1/2 plus c. So c2. So c2 is going to be -1/2. And I don't really want to write it out but you should write it out on the test. Then you would plug those values back in for C1 and C2 to write your final particular solution to this non-homogeneous system of differential equations. Whew. Not that bad though, really, compared to like the other stuff. Like this is really just take what you've already learned how to do with finding the general solution and add on this vector of the equilibrium point. Not that bad. Question. Number 35 from section 10.2. Okay, is it going to be terrible or is it going to be not that bad? Let's find out.
There's 2 ways.
There's 2 what?
There's a matrix when you have like there's 2 ways.
Okay, let's see. 10.2 number 35. Oh, okay, cool. So they're asking us, so here's what they're giving us. The system of differential equations dx dt equal to a times x depends on a real value constant a. I think I was helping someone with this one the other day. Use the eigenvalues to determine the stability properties of the equilibrium at the order. Cool. So we're given a matrix and they're not telling us all of the values. They're basically asking us to find what values of A give you different types of stability or instability. So what we're going to do is we're going to find our eigenvalues based on this, and then we're going to then say what A needs to be to get different, like both positive, both negative, one of each, maybe imaginary. And this probably is a situation where using the trace determinant method to me feels easier, right? We could certainly do determinant of A minus lambda, 1, A minus lambda equal to 0. And then get A minus lambda times A minus lambda minus 1 equal to 0. I guess it's actually not that bad to do it this way. So I've got A minus lambda squared equal to 1. So A minus lambda equals plus or minus the square root of 1, which is 1. And then adding lambda and bringing that over there. Also, when I subtract this over there, it's still like the same thing, right? Because I'm subtracting a plus or minus, it becomes minus plus, but it doesn't really matter which order in this case. So we can say A plus or minus 1 is equal to lambda. That seems way too nice. Let me check the trace determinant method just to be sure. The trace here would have been A plus A, which is 2A. The determinant would be A squared minus 1. So then using the trace determinant method, my lambda should be the trace plus or minus the square root of the trace squared minus 4 times my determinant. And I think it's going to work out real nice. Over 2. That's going to be 2A plus or minus the square root of 4A squared minus 4A squared. Cancels out. And minus 4 times minus 1 is positive 4. All over 2. And yeah, that's 2A plus or minus 2 over 2, which is A plus or minus 1. Okay, good to check. All right, so let's pick some. I feel like A equal to 1 is going to be kind of the breaking point for one versus the other. So let's check a value of A that's like between, yeah. I might test some values here. So like, for example, if A were to be 0, then you get a plus 1 and a minus 1 for your eigenvalues. So A equals 0 means we're going to get a saddle. And same would be true, I think, for any values between -1 and 1. Because if A is between -1 and 1, like for example, 0.99, 0.99 plus 1 is positive, 0.99 minus 1 is negative. Same deal for the other side. If you're just a little bit close to -1, like -0.99, -0.99 minus 1 is negative, -0.99 plus 1 is positive. So for any values between -1 and 1, we're going to get a saddle. Okay. What if A is bigger than 1? I would pick a number. Pick like 3. If A is 3, what are my eigenvalues? Are they both positive? Are they both negative? Is it one of each? Are they complex? Both positive, right? 3 plus 1 is positive, 3 minus 1 is positive. And that seems like it would be true for any value larger than 1, right? You could pick 1.001. Say, okay, well, 1.001 plus 1 is positive, 1.001 minus 1 also positive. So it seems like if A is bigger than 1, they're both positive, which means you have an unstable node. And in a similar way, if A is less than 1, less than 1? No, sorry, less than -1, apologies. Right, like -2 or -3, then -2 plus or minus 1, both negative. -2 plus 1 is negative, -2 minus 1 is negative. So if they're less than 1, -1, both lambdas are negative, and we have a stable node. And you might have seen me studiously avoid the case where A is equal to 1 because it's kind of an issue. If A is equal to 1 or -1, but let's say A equal to 1, our eigenvalues are going to be lambda equal to A plus 1, which is 2, and A minus 1, which is 0. And I will be perfectly frank, I don't really know what we're supposed to say if one of the eigenvalues is 0. Yeah, I really don't know. What we could do is we could look at the graph. Let's do that. Let's plug in A equal to 1 and see what happens when we look at what the direction field actually looks like. I'm curious. Let's see here. Gosh, so many things. Yeah. Where's my graphing thing? Graphing. Let's just use the one that's easier for me to use. Yeah. Is it this one? I think it's this one. Nope, that's not the one. Sorry, that's the wrong one. Is it you? Sorry, I have too many of these. Yeah, there. This is the one this is the easy one to use. So if our matrix is 1, 1, 1, 1, that means our differential equations are 1 times x plus 1 times y, and dy dt is 1 times x plus 1 times y. Let's see how that looks. So let's make a guess. My guess is that since one of them is positive and the other one isn't negative, that I'm gonna get an unstable node. That's what I'm thinking is gonna happen, but I don't really know. Yeah. Okay, I was afraid of this. It's weird. It does look like it's unstable, though. I would say it's unstable. And the problem is one of your eigenlines is essentially like pointing outwards. The other eigenline doesn't point inward or outward because the eigenvalue is 0. So like this line here, this y equals -x, this eigenvector that's -1, doesn't have a direction associated with it because you have the 0 eigenvalue. But you still have an unstable situation. So I wouldn't say node, I would just say it is unstable if A is equal to 1. And my guess would be that if A was equal to -1, that we would get stability in the same sort of way. Let's take a look. I know I wrote something down. You can't see what I wrote down. It's fine. If we go back here and use -1, 1 instead of, so if we change if we take the -x and the -y down there, let's see what happens then. I'm guessing it's going to look the same, except we're going to be pointing inwards instead of pointing outwards. I hope. And I'll feel like I know something. Yeah, cool. So now we're pointing inward towards this line of stability instead of outwards away from it. And you do get, interestingly, not just an equilibrium point, you get a whole line of stability here. Like every point on this line is kind of an equilibrium, which is weird. Neat. Good question, Karen. I like that. Karen, right? Yeah. Sorry. Yeah, it's kind of funky. I remember looking at one of those other ones, and I feel like the corner case where you were at the place where you changed one thing to the other, it felt like the answer in the back of the book seemed incongruous with what I thought the answer should be. Maybe it's wrong. Maybe I'm wrong. I don't know. Okay, we got 10 minutes left. Let's start in on this nonlinear stuff. And I will remind you that the ideas we've seen are still going to hold, meaning that we're still going to find equilibria the same way we've always found equilibria, by setting the derivative equal to 0 and solving for x1 and x2. So let's say we've got the following differential equations. x1 dot equal to 3x1 minus x1 squared minus x2, and x2 dot equal to x1 minus x2. Cool, definitely nonlinear. You've got x1 squared, making that first equation nonlinear, so the whole thing's nonlinear. Basically, if you see anything where it's a power other than like 1, or even if you have like x1 times x2, even though those are both raised to the first power, their product is not a linear thing. So let's start off by finding the equilibria. So we're gonna set each of these equal to 0. And my advice is the same kind of advice I had for when we were finding critical points of function to two variables. It's really kind of a very similar process. Deal with the easier looking thing first. So of these two being set equal to 0, I'm going to look at the second one equal to 0 first. So setting x1 minus x2 equal to 0, that gives me that any equilibrium has to be where x1 is equal to x2. Now, that doesn't mean like everything like that is an equilibrium, right? I'm not going to get 1, 1, and 2, 2, and 3, 3, and 4, 4, and 5, 5, et cetera, et cetera, et cetera. It just means that I'm limited to those sorts of things. But I'm going to be further limited by the other differential equation. So then what I'm going to do is I'm going to sub this in for this equation here. And it doesn't matter which one you pick. I'm going to plug in x1 for x2. So now I'm going to say that 3x1 minus x1 squared minus x1, right, plugging that in for x2 equals 0. And then we're going to try and solve this. So I'm going to say 3x1 minus x1 is 2x1 minus x1 squared equals 0. Factor x1 times 2 minus x1 equals 0. So then we're going to get x1 equal to 0 or x1 equal to 2. And then we go back up here and we say, oh, if x1 is 0, then x2 is also 0. If x1 is 2, then x2 is also 2. So x1 equals 0 means x2 is equal to 0. x1 equal to 2 means x2 is equal to 2. So my two equilibria are 0, 0, and 2, 2. Neat. So now, how do we classify the stability of these two different equilibria? There's not like a 2x2 matrix here that we can just magically make appear because we've got like this nonlinear stuff. So what we have, well, I say that kind of incorrectly because we are going to magically make a 2x2 matrix appear. It's going to be the matrix of second partial derivatives. Well, of first part, I mean, okay. They're second partials, kind of. It's kind of like the determinant of the Hessian thing we did for the classifying a max or a min of a function of two variables. So what we usually do is we just say this first function, we're going to call this f of x1 comma x2 if you really want. And the second we're going to call g. And then we're going to find the Jacobian matrix. So the Jacobian J is the 2x2 matrix of partial derivatives of these things. So it's going to be the derivative of f with respect to x1, and then f with respect to x2, and then in the second row, g with respect to x1, and g with respect to x2. So in each row, you have a different function. In each column, you're differentiating with respect to a different variable. First row, first function, second row, second function, first column, first variable, second column, second variable. All right, well, we can find these partial derivatives. I know it's been a little while since we've done a partial derivative, but it's not been that long. So fx1, let's see, the derivative of f with respect to x1 is going to be 3 minus 2x1 minus 0. The derivative of f with respect to x2 is going to be 0 minus 0 minus 1. Make sure you give yourself enough space between your entries so they look like they're different things. It doesn't look like you're writing 3 minus 2x1 minus 1. Right, it's 3 minus 2x1, and then over here in the other spot, it's minus 1. And then down here, gx1, the derivative of this with respect to x1 is going to be 1. And then gx2, the derivative of g with respect to x2 is going to be negative 1. There's our Jacobian. And then what we're going to do is for our Jacobian, for each equilibrium, we're going to plug that equilibrium into the Jacobian and then use that 2x2 matrix to classify the stability. So let's look at J of 0, 0. That's going to be the matrix 3 minus 0, negative 1, 1, negative 1. So find the eigenvalues. We're not finding the general solution, we're just classifying. Right? No one's usually asking you to find the general solution when you've got a nonlinear thing here. So eigenvalues, determinant of 3 minus lambda, -1, 1, -1 minus lambda equal to 0. So we're going to get, let's see here, 3 minus lambda, -1 minus lambda, minus -1 times 1, 0. Multiplying this out, we get a lambda squared. You always get lambda squared, right? It's always lambda squared. It's never anything other than lambda squared. You get something minus lambda times something minus lambda. And then you have a positive lambda, minus 3 lambda is minus 2 lambda. And then -3 plus 1 is -2. It does not factor. I personally would just use the quadratic formula, right? You could try to do the whole like, is the trace bigger than I could not tell you. Actually, oh, you know what? I could. No, I couldn't. Could I? I know it's going to be a saddle because the determinant of the original matrix is negative. Right? The determinant of that is -3 minus -1, which is -2. Oh, yeah, right. There's the determinant of the matrix right there, -2. But let's still do it anyway, just to be sure. So if we find the eigenvalues here, they're equal to -b plus or minus the square root of -b or b squared minus 4 times 1 times -2 all over 2. So check it out. We've got 2 plus or minus 4 plus 8 is 12. So the square root of 12 all over 2. And this is where you really have to know that the square root of 12 is bigger than 2. It sure is. Square root of 12 is a lot bigger than 2. It's like 3 point something. So that 2 plus root 12 is positive. 2 minus root 12 is negative. So we're getting 1 positive and 1 negative eigenvalue. Which means we have a saddle. So 0, 0 is unstable. And looks like a saddle. Sometimes we don't actually say that the thing is what the eigenvalues would make it, because when you got this nonlinear thing, it's only kind of locally looking like that, and as you move away from it, it's not globally saddle-like. Not satellite, saddle-like. Let's finish this off, and I do want to show you. So just to kind of do the other one here real quick, like j of 2 comma 2, if I plug in 2 for x1, I'm just going to get 3 minus 4. So I'm going to get -1, -1, 1, -1. And then using the trace determinant method, the trace is -1 plus -1. The determinant is 1 minus -1, which is 2. And so then I could never remember this thing for the life of me. So I'm just going to use it and say that my eigenvalues are going to be my trace plus or minus the square root of my trace squared minus 4 times 1 times 2 all over 2. That's -2 plus or minus the square root of 4 minus 8 is -4 all over 2. All right. So at this juncture, based on the square root of -4, we know we have what I'm not going to ask about stability yet. I'm just asking, do we have a saddle, a spiral, or a node? Spiral. Okay, based on this number out here, is that spiral stable, unstable, or neutral? Stable, because we have a negative real part there. So stable spiral. Or I would just say the 2-2, the equilibrium 2-2 is stable. Now, just so you can see what this looks like, because I do think it looks kind of cool, let's take a look real quick and go back to our thing here. So if I plot this real quickly here, I've got my differential equations were 3 times, I hate the only thing I don't like about this one is I have to write the times symbol. 3 times x minus x squared minus y, and then the other one's going to be x minus y. Awesome. And if you graph it, ooh, that's neat. So near 0, 0, we have kind of saddle-y behavior. But near 2, 2, we have stable spiral behavior. Cool. Really cool. I think it's really neat. So that's what's going on with these nonlinear systems of differential equations. You're often getting multiple equilibria, and each equilibria has its own sort of local behavior that's true close to it. But as you move far enough away, like way over here, you're just kind of getting, I don't know, I guess kind of saddleish behavior. But over here, you get wild things happening. So, and then in the middle here, it's like, ish, what's going on? Oh, no, I don't know. Okay, so anyway.